Welcome back to Salts of the Earth, an 8-part video series on issues related to salt attack in adobe and earthen structures. My name is Eric Liefeld, and I'm with Mesilla Valley Preservation. Previous videos in our series have covered salt attack, so hopefully you have a good understanding of what causes salt attack and how to recognize it. In this video, we'll look at MVP's tools and process for accurately detecting and measuring salts in the field. This video will focus on sample collection, sample processing, and analysis. There are other live-action videos in this series that document both sample collection and processing for those who want a more in-depth description. As we looked at goals for designing our salt processing kit, the fundamental desire was to know where the salts were concentrated, so that we could understand existing conditions and target salts for removal. Because salts are often a footprint for how moisture has moved in a wall, they can also give us useful forensic insights into existing conditions in historic adobe walls. We've seen in previous videos in this series that salts are constantly on the move, largely depending on prevailing relative humidity. If we are going to target salts for removal, we first have to know where the bulk of the salts are located at any given point in time. This means that we need tools that can give us an accurate and rapid answer in the field, ideally the same day that samples are taken. We also want tools that can measure different types of samples. For instance, you might want to simply compare a suspect sample with a known baseline, or compare soil samples from different locations. Or you might want to verify that new materials aren't bringing in high concentrations of salts. In this presentation and in our demonstration videos, we'll be showing how to take core samples of existing adobe walls. This core sampling process can be adapted to other kinds of masonry as well. We also wanted the toolkit to be low cost and as simple to operate in the field as possible. Ultimately, our goal is to describe an inexpensive field test kit that contractors and preservation specialists can put together to suit their needs. You'll notice that our emphasis is on off-the-shelf components and not proprietary tools and methods. Importantly, this toolkit is still a work in process that we are still refining. This photo illustrates the sample collection portion of MVP's salt field kit in front of a salt-affected wall. The sample collection kit includes a prototype coring tool that mounts in a standard cordless drill. The coring tool is made from readily available components that allow for sampling at specific intervals. The sample collection kit and process are designed to minimize cross-contamination of samples so that we can get the most accurate results. The sampling kit intentionally contains simple components that can be obtained at any hardware store. The drill bit used in our prototype sampling kit is a 5/8 inch masonry bit in an 18-inch length. Different diameter masonry bits could also be used, but we found that the 5/8 inch bit worked well for our purposes. Another essential component of the sampling kit is a collection tube that is closely mated to the diameter of the drill bit. In our case, we used a simple piece of 1/2-inch copper pipe. The collection tube must slide easily onto the drill bit, allowing the head of the masonry bit to protrude at least a little to the diameter of the tube. This arrangement lets the tube closely follow the head of the masonry bit into the hole as it is drilled. Loose material then collects in the tube for sampling. A vacuum cleaner with a customized attachment is used to avoid cross-contamination of samples. In our case, a 1/2-inch PVC pipe was adapted as a vacuum cleaner attachment. Simple Ziploc bags labeled with a Sharpie can be used to collect samples. The core sampling process involves carefully advancing the sampling tool into the wall in 1-inch increments, while holding the collecting tube steady. The sample is then retained in the collection tube. Removing the sample from the collection tube is as simple as reversing the drill direction while holding onto the collection tube. The process has the function of homogenizing the sample into a fine powder. Because salt concentrations typically increase toward the surface of the wall, it is particularly important to try to avoid cross-contamination of samples. For this reason, we vacuum loose material from the hole using a specialized attachment between each sample. At that point, the process is repeated for the next 1-inch increment, continuing to the desired depth of the core sample. Our sample processing is done with an accurate digital balance and relatively inexpensive and portable off-the-shelf conductivity meters. These items are commercially available from a number of vendors. The conductivity meter features a sensitive probe that measures the electrical conductivity of a given aqueous solution. This is an ideal tool for our sample processing purposes because conductivity varies with the salinity of the solution. For example, distilled water has essentially zero conductivity, while seawater has substantially greater conductivity. It is important to choose a meter that is sensitive in the desired range. The meter used in our preliminary testing was an Oakton Con 6 Plus handheld conductivity meter. Our process also involves calibration of the meter to compensate for any non-linearity in the signal produced by the meter. Dr. David Rockstraw is our principal investigator, and he designed our sample processing kit to be portable and as simple as possible to operate in the field, while retaining considerable precision. Dr. Rockstraw is Department Head of Chemical Engineering at New Mexico State University in Las Cruces, New Mexico. Here Dr. Rockstraw is processing samples with our portable laboratory. Other than the tools mentioned, a laptop, tablet, or smartphone can be used to record and graph results. For the conductivity meter to be useful for our purposes, we need to make sure that the tool is capable of measuring what we think it is measuring, at the concentrations that we will be encountering in our sample processing. This is a typical chart showing calibration and linearity curves for a conductivity meter. In this case, the meter was used to measure both sodium chloride and potassium iodide in standard aqueous solutions of known concentration. A resulting calibration curve was applied to the results. The calibration curve is then built into software tools to apply to results. Of course, it is helpful to calibrate the conductivity meter with the actual salt you will be measuring in the field. For our testing, that salt has been sodium chloride. Detailed sample processing is beyond the scope of this video, but it is covered in more depth in several live-action videos in this series. Basically, after calibration, a small amount of each sample is mixed with distilled water, with precise weights for both. The probe then measures the salinity of the sample. Software then calculates an equivalent of salt to adobe mass ratio for each sample. Software automatically compensates for the calibration information, taking into account the linearity of the conductivity meter for measuring the specific salt of interest. In the interest of showing our work, here are the fairly simple calculations used to compute salinity for each sample. All of these calculations are easily performed in software. For our testing, we utilized a simple spreadsheet. Ultimately, we want to know the number of grams of salt compared to the number of grams of adobe for each sample. First, we want to determine the calibration constant using distilled water and a known concentration of salt. Equation 1 represents a linear equation that relates salt concentration to the measured conductivity. The relationship between these quantities is the calibration constant C. The calibration constant can be found from equation 1 as the quotient of the standard solution concentration divided by the measured conductivity of the standard. When creating a standard, it is desirable to identify the standard concentration that yields a measured conductivity of about 75% of the full range of the probe. With the Oakton Con 6 Plus meter, the manufacturer's stated range is 0 to 200 millisiemens. MVP determined that a solution of about 0.15 grams of sodium chloride per gram of water yields a reading of about 175 millisiemens, which provides a sufficiently linear and wide range of use for the probe. A more accurate representation of the measured salt loadings can be obtained by using a multi-point calibration and polynomial representation of the resulting regression line. Equation 2 uses the calibration constant, which was calculated in equation 1 to estimate the ratio of salt to adobe in samples of unknown salinity. This calculation is based on the product of the calibration constant with the measured conductivity from the unknown sample, divided by the ratio of the mass of the adobe sample material to the mass of the water used in sample preparation. Again, a full treatment of this process is shown in a later video in the Salts of the Earth series. After processing all of the samples from a given core sample, the result of our efforts is a salinity gradient, as shown in this slide. In this case, two roughly 10-inch core samples were drilled from either side of a 36-inch adobe wall in the Nestor Armijo house in Las Cruces, New Mexico. Together, the two salinity gradients approximate an exponential curve, with concentrations of salts rising dramatically toward the surface of the wall. We now know precisely how salt levels are concentrated in the wall at the vertical and horizontal location of our core sample. This information can be very useful in interpreting existing conditions and understanding how both moisture and salts have been moving in an adobe wall. This information is also very important for helping us to think about remediation approaches. Since salts are constantly on the move, the salinity gradient also gives us a data point for visualizing changes over time, as part of ongoing monitoring and maintenance. We'll come back to this particular curve in one of our case studies in the next video in the series. In this video, we've provided an overview of MVP's field toolkit and shown how it can be used to collect and measure salts in the field. The next video in the Salts of the Earth series will talk about remediation approaches for salt attack, along with several case studies. Thank you for joining us, and please visit MVP's YouTube channel for more videos in the Salts of the Earth series, where these techniques are shown in detail.